All right, so today we're going to be talking about radical equations and how we solve them. So the first thing, that I want to talk about is what is a radical equation. Okay, so a radical equation is an equation, I'm going to switch to black, that has a variable in the radicand, right? So if you think about like the square root of n, this is the radicand. Okay. Okay, so how do we solve these things? Well, we can solve them algebraically or we can solve them graphically. We're going to talk a lot more about the algebraic piece a little later on. We're going to talk about graphically in a minute. But one thing that I want to really emphasize is that the algebraic solution will always get you exact values. And if your solutions are irrational numbers, then graphically you will only get approximate values. So you need to watch out for that. If you are asked for exact values, you have to solve algebraically, okay? The other thing that's really important to keep in mind is you have to check for extraneous roots. And the reason for that is that in the process of solving these equations, we're going to be changing the nature of the equation from radical to either quadratic or linear. And it's possible to get a solution to a quadratic equation that is fine in the quadratic equation, but doesn't work in the radical equation. So everything has to be verified. Okay, now graphically, there's two ways that you can solve graphically. I would say that I personally use one way more than I use the other. Essentially, you can either graph y1 equals the left side and y2 equals the right side, and then find the x value of the intersection point. So that's usually what we do. The other thing that you can do, though, is equate one side of the equation to 0. And then graph. And then what you would be doing is you'd be looking for the x-intercepts or the zeros of that function. Okay, so we're going to start out with an example that we're going to solve graphically. If I were to solve this one, x plus 3 equals the square root of 12 minus 2x squared, by graphing y1 equals one thing and y2 equals another thing, then I would put in y1 equals x plus 3, y2 equals the square root of 12 minus 2x squared. And then I'm looking for an intersection point. Now, unfortunately, I'm recording this on my iPad and I don't have a graphing calculator application on here. So you're gonna have to kind of take my word for it as to what these look like. But I mean, the first one is a linear function. So hopefully you guys can get your heads around that. Y1 has a y-intercept of 3, y equals x plus 3, and a slope of 1. So there's y1. The second function, when you graph this, looks something like this. Oh, I'm sorry. Oh no, that's good. That's right. Okay, looks something like that. Okay, so there are in fact two intersection points here and here. And you would have to go through, you know, second calc number 5 for intersection on your graphing calculator, but I'm going to ask you to take my word for it. The x values of the intersection points are negative 2.41 and 0.41. Right? So right here, that's the negative 2.41, and this is the 0.41. Okay? Now, the other thing that you can do is equate one side to 0. So let's suppose I made the left side of the equation 0. Here's the equation right here. So I'm going to subtract x and 3 from the left side. Well, then I'll have 0 on the left side equals the square root of 12 minus 2x squared minus x minus 3. And if I graph that, then the graph looks something like this. Okay, roughly. The x-intercepts, however, are still the same values. Now I essentially want to know, where is y1 equal to 0? Because that's this side of the equation. So I'm looking for the x-intercepts, the values of x that make y equal to 0. And those have the exact same values. So here, same solutions, negative 2.41 and 0.41. You would just press something different on your calculator because now you're looking for zeros as opposed to intersection points. Okay, so graphically, not a ton new there. I tend to just use the first method where you graph y1 equals left side and y2 equals the right side, and then look for the points of intersection. I'm just going to turn this into airplane mode so that I don't get alerts on here. Okay. Let's talk about algebraically. Okay, so algebraically, essentially what you want to do is first, when you're dealing with radicals, remember that you have to have a positive radicand. So make sure you state your restrictions. Right? So for example, if there's like a square root of x in there, then x would have to be greater than or equal to 0 because you want that radicand piece to be positive or 0. Second thing that you're going to do, I think I'm going to actually also have to turn my Wi-Fi off, there we go, is isolate the radical. Make sure that the radical is by itself on one side of the equation. And then square both sides. Okay, when you square both sides, you won't have a radical anymore. You're going to have either a linear or quadratic equation. So at that point, you can solve for x. Okay. And then finally, you need to check for extraneous roots. Okay, now this is a bit of a complicated process though, because you have to take into account the restrictions from step 1, but also when you're dealing with radical equations, you can have additional extraneous roots that sort of seem to come from nowhere. And the reason that they occur is that, let's say you take a look at, -5 and 5, for example. When you square those, they're equal to one another, but originally they're not. So originally you're working from the place in a radical equation where you don't square both sides. And so essentially what you need to do is verify every solution that you get by substituting it back into the original equation and make sure that the left side does in fact equal the right side. Okay, so let's look at some examples. Okay, so we have this first equation, 7 equals the square root of 12 minus x plus 4. The first thing that we're going to do is isolate, or actually, sorry, the first thing we're going to do is state the restrictions. Okay, so here the restriction is, well, we need 12 minus x to be greater than or equal to 0. So if I isolate x there, let's say I subtract 12 from both sides, negative x is greater than or equal to negative 12. When I isolate x by dividing by negative 1, the direction of the inequality is going to flip. So x has to be less than or equal to 12. There's my restriction. Okay. Second, I need to isolate the radical. So I have 7 equals square root of 12 minus x plus 4. So I'm going to subtract 4 from both sides. And when I do that, 7 minus 4 is 3 equals the square root of 12 minus x. Okay. And at this point, I want to square both sides. Okay, so on the left side, 3 squared is 9. On the right side, square root of 12 minus x squared is just 12 minus x. Okay, and from here, right, think, okay, 9 equals 12 minus 3. So x has to equal 3. Okay. Now, at this point, you need to check a couple of things. Number one, is 3 less than or equal to 12? That goes back to your restriction from from the first step, okay? But sometimes you will get solutions that even meet those restrictions and they still don't work, because what you'll end up with is the left side and the right side will have the same magnitude, but they'll be negatives of each other. So you might have one side equaling negative 5 and one side equaling 5, for example. Okay, so I'm actually going to check by, actually I'm going to erase this. So I'm going to check by looking at the left side of the equation and the right side of the equation. Okay, and subbing in the value of x equals 3 to both sides. So on the left side, it's always just equal to 7. On the right side, I'm going to get the square root of 12 minus 3 plus 4. That's the square root of 9 plus 4, and that is 3 plus 4, which is, in fact, 7. Okay, so we have that the left side equals the right side here, so we're good. Okay. B. All right, so for B, we have x plus 3 equals the square root of 12 minus 2x squared. So first thing I'm going to do is focus on the restrictions, and I'm going to try and do it up here because I'm running out of space. But essentially for this question, what I need is that radicand, 12 minus 2x squared, has to be greater than or equal to 0. Okay, so to figure out, this is actually a quadratic inequality. To figure out where the values of x will sort of work, almost think about what it would look like if you were to graph this. If you were to graph y equals 12 minus 2x squared, then it's a parabola. The y-intercept is 12, and it opens down. So essentially, where's that larger than 0? It's between these 2 points. So what we need to do is figure out what those zeros are. Okay, what value of x makes that 0? And that will tell us what the restrictions have to be. So I'm going to set this equal to 0. So that I can find these two values, and also for x. So here I'm going to have 2x squared equals 12, x squared equals 6. So if I solve for x, I'm going to get that x equals plus or minus the square root of 6. So this guy over here is negative root 6. This guy over here is positive root 6. So my solution, or my restrictions rather, are that negative root 6 has to be less than or equal to x, which is less than or equal to root 6. Okay? Now, we actually solved this graphically a few minutes ago, and so we know that there are two solutions. This is the exact same one that we graphed, okay? But ordinarily, you wouldn't know that, and so you need to go through this process to make sure if you're showing algebraically, you have to algebraically show what the restrictions are, okay? So what I'm gonna do to solve this is I'm gonna start by squaring both sides. Okay. Now x plus 3 squared is x plus 3 times x plus 3. So when you're working on the left side, keep that in mind because you have to expand that full binomial times binomial, right? So you're going to get x squared and then plus 3x plus another 3x is plus 6x plus 9 equals 12 minus 2x squared. Hopefully you have enough room to do this. Now this happens to be a quadratic equation. So with a quadratic equation, the goal is essentially to equate one side to 0. So I'm going to maybe subtract 12 and add 2x squared to both sides. And then my left side will be 0. I'll have 3x squared on the right side plus 6x minus 3 equals 0. And at this point, once you equate to 0, to solve this equation, you either need to factor it if possible. These don't always factor. Or you may at this stage need to use the quadratic formula. Now, one thing that I'm going to do to make my life a little easier is I can see that on the left side, there's a numerical greatest common factor of 3. So I'm going to divide both sides by 3 so that the coefficients and the constant are a little bit smaller. So 3x squared over 3 is x squared, 6x over 3 is plus 2x, and then negative 3 over 3 is minus 1. That equals 0 over 3 is still 0. Okay. Now, if this is factorable, I'd be looking for two numbers that multiply to negative 1 and add to 2. And we actually can't find two numbers that do that. Okay, so this is not factorable. That doesn't mean that there's no solutions. What it means is that if there are solutions, they will be irrational. Okay, so I'm gonna have to use the quadratic formula here. Now that is on your formula sheet, so you don't have to have it memorized. But we are going to have to utilize it sometimes. So my solution to this type of equation is x equals, the quadratic formula is x equals minus b plus or minus root b squared minus 4ac all over 2a. Okay, so negative b, that's minus 2 plus or minus the square root of b squared, 2 squared, minus 4 times 1 times negative 1. Ooh, I'm really running out of space here. I apologize. And that's all over 2a, 2 times 1. Okay, so when you simplify that, you will get negative 2 plus or minus 2 squared is 4 minus 4 times 1 times negative 1. So negative 4 times 1 times negative 1 is plus 4. So that's going to be 4 plus 4, which is root 8 over 2. Okay, now if you get to this stage, that's pretty good. But this actually can be simplified further because the square root of 8 as a mixed radical is 2 root 2 over 2. Because 8 is 4 times 2, so you can pull that perfect factor, or perfect square rather, of 4 out of the radical. Square root of 4 is 2. Okay, and this can be simplified even further because we can divide each term in the numerator by 2. And what we end up with is x equals negative 1 plus or minus root 2. And in fact, that is the same answer that we got when we solved this graphically. -1 minus root 2 is negative 2.41, roughly. And -1 plus root 2 is 0.41, which is what we just saw when we solved it graphically. This would be an exact solution, however. Okay. So we are going to try another one where we're going to try and solve this both graphically and algebraically. And this particular equation, square root of x plus 3 minus 2 equals 0, I could ask you to solve that graphically by hand without the use of technology. Okay? And what we're going to have to do here is use our knowledge of transformations to be able to graph this thing. Okay, so if I graph, one side is already 0. If I graph y equals the square root of x plus 3 minus 2, okay, compared to, I'm going to do this one in a different color, y equals the square root of x, this guy has a horizontal translation of 3 left and a vertical translation 2 down. So if I wanted to graph this function by hand, I could start by graphing y equals root x. So I'm going to put those points in 0, 0, 1, 1, 4, 2, square root of 4 is 2, and 9, 3. And each of those red points, I'm now going to move 3 left and 2 down. So this point is going to go 1, 2, 3, 1, 2. This point, 1, 2, 3, 1, 2. This point, 1, 2, 3, 1, 2. This point, 1, 2, 3, 1, 2. Okay, and there is my new graph. My transformed graph. Now in this case, I want to know when that is equal to 0. So I can look at, okay, where is y equal to 0? That happens right here. And so the solution has to be x equals 1. Okay. Now algebraically, I've got the square root of x plus 3 minus 2 equals 0. Okay, so think about restrictions first. I need x plus 3 to be greater than or equal to 0. So if I subtract 3 from both sides, x has to be greater than or equal to negative 3. Okay, what I'm going to do next is isolate the radical. So I'll add 2 to both sides, and I will get the square root of x plus 3 equals 2. And at this stage, I can square both sides. And when I do that, I will get x plus 3 on the left equals 4 on the right. And so I can subtract 3 from both sides, and I end up with x equals 1. Okay. Now, you should be checking these, particularly if you're only solving them algebraically. You know, we have the graphic solution as well, so we know that x has to equal 1. But even if it meets this restriction that x has to be greater than or equal to negative 3, you should still check. Right? So what I'm going to do is put in my equation square root of x plus 3 minus 2, and minus 2. The right side is 0. Okay, so the right side, nothing to do there. That's just 0. On the left side, I'm looking for what's the value of the square root of 1 plus 3 minus 2. And that is the square root of 4 minus 2, right? 2 minus 2, that is 0. And so we're good. The left side equals the right side. Okay? All right, so we're going to do a couple more questions. First question, solve this equation, 4 minus x equals the square root of 6 minus x, both graphically and algebraically. Okay, so graphically, I'm going to graph y1 equals the left side. Whoops. and y2 equals the right side. Okay, now for the first graph, y1, this is a linear function. The y-intercept is at 4, and the slope is -1. Okay, so there's y1. y2, well, we have to do a little bit of work here because to figure out the transformations that have occurred to my base function of y equals the square root of x, I need to sort of rewrite this with the coefficient of x being 1, because then I can figure out that b value, and I can also figure out my horizontal translation. So I'm going to rewrite this as negative. I'm going to factor the negative out from the x minus 6. Okay, if I distributed this back in, I'd get negative x, and then negative 6 is plus 6. So it is equivalent. But in this format, I can see, okay, compared to y equals the square root of x, there's been a horizontal reflection in the y-axis, and I've moved 6 right. Okay, so for example, again, if you wanted to plot this by hand, I would start out by plotting a few points for the original function, and then think, okay, let's say I horizontally reflect these. Now what'll happen is they're all going to be on the negative side. So -1, 1, -4, 2. It looks like that's all that I'm going to get. 0, 0 won't go anywhere. Maybe I'll just put those in a different, using an X that you can see the difference with the reflection. So that's the reflection first. Then I need to move all of those 6 right. So I'm going to take this guy and go 1, 2, 3, 4, 5, 6. And I'm going to take this guy and go 1, 2, 3, 4, 5, 6. And this guy, 1, 2, 3, 4, 5, 6. Okay, and there is my graph. Okay, I can see the intersection happens when x equals 2. So that is my solution. Okay, now algebraically, first let's start with restrictions. So we're looking at the square root of 6 minus x. Even based on the graph, we can see that x has to be less than or equal to 6. Okay, but remember, you can always figure that out by saying radicand has to be greater than or equal to 0 and solve for x. Okay, so I'm going to put down my equation. 4 minus x equals the square root of 6 minus x. And then radical is already isolated, so I will square both sides. Okay, and remember, 4 minus x squared is 4 minus x times 4 minus x. So when I expand here, 4 times 4 is 16. And then minus 4x minus another 4x is minus 8x. Negative x times negative x is plus x squared. So I'm going to rewrite that just in the format x squared minus 8x plus 16. I'm just going to change around the order of the terms because that's kind of the way I'm used to it. And then on the right side, square root of 6 minus x squared is 6 minus x. Okay, now this is quadratic, so I can now equate one side to 0. So I'm going to subtract 6 and add x to both sides. And then what I'm going to see is that the right side equals 0, the left side is x squared minus 7x plus 10. And this one is quite nice because it factors, so we do not need to use the quadratic formula, which is always a good thing. I can factor this into x minus 2 times x minus 5 equals 0. And from factored form, I can say, okay, x has to equal 2 or x has to equal 5. Okay. Now, we know from the graphic solution that we only got x equals 2. That's all we got. We did not get x equals 5. And x equals 5 is actually within the domain. So there's no problem with that. So we really need to see what's going on here. And this is really what I mean about making sure that you verify everything. Okay, so what I'm going to do is, I think I'll do it up here if I have some space. Ooh, I might not. Okay, let's see. I think I can make this bigger and then that'll work. So I'm going to verify. Right? And I got two solutions to the equation. X equals 2. Okay, now if I verify that in the original, the left side was 4 minus x. The right side was the square root of 6 minus x. So if I sub a 2 into each of those sides, left side's 4 minus 2, that's 2. The right side is the square root of 6 minus 2. Okay, now square root of 6 minus 2 is the square root of 4. Square root of 4 is 2. So that's good. These are equal. If I verify x equals 5, however, let's see what happens. Okay, on the left side, I'm going to have 4 minus 5 rather, which is negative 1. On the right side, I'm going to have the square root of 6 minus 5, which is the square root of 1, which is 1. And these are not equivalent. Therefore, this solution of x equals 5 is extraneous, and we need to cross it off. Okay, so these can be very tricky because, you know, we tend to just look at the restrictions, which is x has to be less than or equal to 6, but there's actually more to it than that. And so what I really want to emphasize is just verify everything. Plug every answer that you get back into the original to see if your answers work, right? Left side has to equal the right side. Okay. So, a couple more questions. The equation, the square root of x minus 5 plus 4 equals 1 has no solution. Verify this both graphically and algebraically. Okay, so graphically, I could graph the left side and the right side, right? The left side, whoops, square root of x minus 5 plus 4. Okay, that's a transformation of the square root of x, and all that's happened is it's been translated. It's been translated 5 units right and 4 up. So these points, I'm just going to do a couple of them. 4, 2. I'm going to move those each 5 right, so 1, 2, 3, 4, 5, and up 4. 1, 2, 3, 4. This guy, 5 right, 1, 2, 3, 4, 5, up 4, 1, 2, 3, 4. And this one, 5 right, 1, 2, 3, 4, 5, up 4, 1, 2, 3, 4. Okay, so there is my new graph. So that's y1. y2 equals 1, which is just a horizontal line over here. Okay, these will never intersect. Therefore, there's no solution. Okay? Algebraically, I have the square root of x minus 5 plus 4 equals 1. Okay? Let's say I isolate the radicals, subtract 4 from both sides. Sorry, that's an equal sign. I'm going to have the square root of x minus 5 equals negative 3. Okay, now at this stage, I can actually tell that there's not going to be a solution anyway, because the left side is positive and the right side's negative. So that doesn't work. A positive number cannot equal a negative number. But even if you did square both sides, and you get x minus 5 equals 9, right? Add 5 to both sides, x equals 14. If you plug that in to the original equation and try and verify, right? Right side's equal to 1. This is the square root of 14 minus 5 plus 4. That's the square root of 9 plus 4, which is 3 plus 4. That does not equal 1. That equals 7. So that solution doesn't work. Okay? All right, last question for today. Determine the initial velocity required for a roller coaster design if velocity is 26 meters per second at the bottom of a 34-meter drop. V equals the square root of V naught squared plus 2AD, where V equals velocity, D equals drop, and A equals 9.8 meters per second squared. Okay? So this is essentially a situation where you're given an equation with, 4 unknowns, V, V naught, A, and D. You're given 3 out of 4 of them, and you need to solve for the 4th. Okay, so we want to determine the initial velocity. That's V naught. That's what we want to know. Okay, for a roller coaster design, if the velocity, that's V, is 26 meters per second, at the bottom of a 34-meter drop, that's D. And then we're also told that A, acceleration, is 9.8 meters per second squared. And for now, I know your physics teachers will probably roll their eyes at me. I'm going to leave the units out. Just make sure at the end of the day, I'm looking for an initial velocity, so my units should be meters per second squared. Okay, I know in the physics world, they will tell you to do unit analysis for everything, but I'm going to be lazy with that. And I'm just going to plug everything that I know into this equation, right? So I know V, that's 26, equals the square root of V naught squared. I don't know that. Plus 2 times 9.8 times 34. Okay, now when you go to solve this, the radical has already been isolated. So I'm just going to square both sides. 26 squared, I don't know this off of the top of my head, but I've already done this. That happens to be 676. And we're going to end up with V naught squared plus, so 2 times 9.8 times 34 is 666.4. Okay, so if we subtract 666.4 from both sides, this works out to be 9.6 equals V naught squared. Okay, now technically if this was just an equation with no context, you would say that V naught has to equal plus or minus the square root of 9.6. Okay, however, actually I'm going to do it this way. I'm going to write it out not as plus or minus, but as negative root 9.6 or positive root 9.6. Okay, and then we can cross this one off because that doesn't make sense in the context of the question. The initial velocity is not going to be negative. Okay, so square root of 9.6 is about 3.1 meters per second. Okay, so I'm going to leave it there and we will continue